The gradient of a straight line is easy. Pick 2 points, rise over run, done. But a curve betrays you. Its steepness changes at every single point, so which gradient do you even mean? Calculus answers with one audacious move. Zoom in close enough, and any smooth curve starts to look perfectly straight. That zoomed-in steepness, the gradient at a single point, is called the derivative. It is the whole of this unit in one idea. Measure how fast a curve is rising right here, right now. Master that, and tangents, turning points, and optimization all fall out of the same machine. Let's build it. Here is the trick that started calculus. Take your point, and a second point a little distance h away. The straight line joining them, the chord, has a gradient you can actually compute, the change in y over h. It is an approximation, but a workable one. Now slide that second point closer and closer, shrinking h toward 0. The chord pivots, swinging until it just kisses the curve at one point, the tangent. The gradient it settles on is the derivative. We write it as the limit, as h tends to 0, of f of x plus h minus f of x all over h. Doing that limit by hand every time would be exhausting, and mercifully you almost never have to. For any power of x, there is a one-step rule. Bring the power down to the front as a multiplier, then knock the power down by 1. That is the entire engine of pure 1 differentiation. So x cubed differentiates to 3x squared. The 3 drops down, the power falls to 2. Constants simply vanish because a flat horizontal line has 0 gradient. Differentiate term by term, and even a long polynomial surrenders in seconds. This is the rule that earns its keep on every paper. The derivative hands you the gradient at any point you like. Plug in the x value, and out comes the slope of the tangent there, the straight line that grazes the curve, matching its direction exactly. From a gradient and a point, you already know how to write the line's equation from coordinate geometry. The normal is the tangent's perpendicular partner, cutting straight across the curve at a right angle. Its gradient is the negative reciprocal of the tangents. Flip it over, change the sign. The same -1 over m trick you met with perpendicular lines comes back for an encore. Now the derivative becomes a lie detector for the curve's behavior. Where the gradient is positive, the curve is climbing. Where it is negative, the curve is falling. And exactly where the gradient hits 0, the curve pauses, momentarily flat. Those flat spots are the stationary points, and they are where all the interesting things happen. To find them, you do exactly what that sentence says: set the derivative equal to 0 and solve. Every maximum, every minimum, every turning point a question can ask about hides at a solution of dx equals 0. Differentiate, set to 0, solve. That 3-step ritual answers most of the unit. A stationary point could be a hilltop or a valley, and you need to tell them apart. Differentiate a second time to get the second derivative, which measures how the gradient itself is changing. If it is negative, the curve is bending downward, so you are on a maximum. If positive, bending upward, a minimum. And this is what powers optimization, the most useful trick in the unit. Want the largest volume from a fixed sheet of card or the cheapest design? Write the quantity as a function, differentiate, set it to 0 to find the turning point, and the second derivative confirms whether you have found your maximum or your minimum. Real problems, same machine. Here is the whole unit on a single page. On the left, the big idea. The derivative is just the gradient of the curve at a point. The rate of change you find as a chord shrinks down to a tangent. In practice, you never grind that limit. You reach for the power rule. On the right sits the toolkit that all flows from it. The derivative's value is the gradient of the tangent. The normal is perpendicular, so its gradient is -1 over that. Set the derivative to 0 for stationary points, and the second derivative tells you a maximum from a minimum. Your drill underneath is just 4 steps. And the boundary fence so you do not overvise. The chain, product, and quotient rules belong to pure 3, along with differentiating sine, cosine, e to the x, and natural log. Integration is the very next unit, not this one. So differentiation is gradient, power rule, tangents, and turning points, and nothing fancier.